what is going on. Um, let's get into it. So for this problem, recursive voting, rank list of votes representing election votes for candidates A and candidate B. Each element of votes represents a vote to one of two candidates. If there's less than zero, it's a vote for A. If it's greater than or equal to n, which is the length of votes, then it's vote for B. Otherwise, a vote at index I made the same vote as this, which is basically just going to get the value at this current one and go to the index for that one. Return the number of votes that candidate A received. You can assume all votes are eventually made to either A or B. And we're in is the length of votes. So you have 2, -1, 5, 1, 3. So basically for this one, so the idea is I think we're going to want to use a union find. So when you have 2, -1, 5, 1, 3, this is a particularly not a super illustrative example. We could switch this to something like this. And basically what I do is I iterate through, I find everything is -1 because I want to count the number of votes that are for A. So I would go here, I would say, okay, for A we have -1. And then I would see 3, and I would say 3 doesn't make sense. So what I would do is I'm going to create an array, but I need to keep track of where the index was. 0, 1, 2, 3, 2, 4, 3, 0. So I'm going to do is I'm going to pop this out and say, hey, this is a 1. Let's see, it should map to one of the candidates. And I say, sorry, I should push back the index. So 1. I say, okay, well, the 1 is candidate A. So that means I want to add 3 to this set. And then I go to 2. And, 2, I say, doesn't point to candidate A. And I say 3. So 3, I say, okay, well, 3 points to 3. So who's the parent for 3? It's 1. So that means I add the 0th index in here. Now, what if this was a 1? Then I'll say, what's the parent to 1? I'll say it's 1. So I'll add in the 0 into this disjoint set. And then just count the length of A. Um, so I'll just do this straight up union find algorithm. Okay, so if we do a straight up union find algorithm, we need our struct union find. We'll need our vector int parents, our sizes. Oops, using the wrong language. Void init. This is so that I can initialize this. Start it at 0 iota, so it's going to label the parent as the current index. And sizes, we're going to assign the 0th value to, or sorry, we should evaluate, they should all be 1 at the beginning. Okay, and then we need our two functions. Our two functions are going to be int find, so as per the name find. Basically, if I is equal to the parent of I, you want to return I, else you want to return that the parent of I is equal to find the parents of I. Parents, okay. And then, oh, right. And I call this ufind. That's just what I call it in C++ because you can't use union. See how it's red? There's already a function exists, so I just add a UU in front of everything. So int I, int j, we want to union these two nodes. Basically, if I guess, oh well, here's what I do. I'm gonna say I equals find I, so I'm gonna find its parent, and j equals find j. So basically, I'm gonna find their parents, which also tells me what disjoint set they belong to. If they don't belong to the same disjoint set, we're going to do this. Otherwise, we return return false. I say false as in I did not union them. This one will return true as in I did union them. And if we union them, what we want to do is we want to check if sizes j happens to be greater than sizes I, then I want to swap I and j. And then basically what we're going to do is we're going to set the parents of j to be equal to I, if that makes sense. So we're basically saying, hey, we're attaching this disjoint set that has the root node to be j. Now we're going to say set its parents to be equal to I, which is a root node for another disjoint set. In particular, I is guaranteed to be the larger disjoint set because I swapped them here. And if I'm going to do that, then I also need to upgrade the size. The sizes for I will be now equal to the sizes of j. Right, so the size of wherever the disjoint set that point to j was at that root node is now going to be added to the size of the disjoint set that contains the root node, which is I. So that's union find structure. Okay, so we did that. Now what we want to do is we want to actually like start parsing the votes. So one thing I want to do with these votes is their numbers, but I want to find which ones are for candidate A and add them to a disjoint set. So we're going to ignore anything for candidate B, and we're just going to add everything for candidate A. So what I'm going to do is I'm going to say for int v and votes, and basically, hey, if v, oh, wait a second. Okay, yeah, so what I'm gonna do, actually, it's gonna be kind of different. Actually, usually this is how I would initialize my parents, but I'm gonna initialize my parents differently in this problem. So what I'm gonna do is I need to have them initialize to be set equal to what I guess candidate are for. So if they're for candidate A, I want their parent to be -1. So I'm going to do parents dot assign, and let's say -2. We'll say uh, -2 signifies it is B initially. Which reminds me, I need to create my union find data. So I was going to say disjoint sets, and then init in. And let's just vote size. And then basically if v is less than 0, we are going to update the parent. We are going to say that um, uh, we're going to say, hey, the DS parents for this node, the DS parents for this particular index, which is why this should be indexes. So if this one is less than 0, this particular index parent should be equal to -1. And this is tricky because I want the sizes to be correct. Okay, so actually maybe we'll just say, hey, we'll add 2 here, and we'll add 2 here, and then we'll say, hey, if you're in, you're for candidate B. If your value is n plus 1, then you're for, oh no, it should be n. If so, let's say n candidate B initially, or let's do n plus 1. So n plus 1 here for candidate B. The size for each of these should be 1. Well, not exactly though. So the last one, so the sizes for n should be 0, and the sizes for n plus 1 should be 0. Uh, um, I think that's pretty straightforward. And I think that's what I'll do. So here, we're going to set its parent to be n, and we're going to say ds.sizes and plus or equal to 1. So actually, basically what I'm doing is I'm doing ds.union I with, shit, it's not going to work because I have this size thing. Um, yeah, okay, I can't use union, so I have to just do this. So I just have to say, hey, I'm going to set the parents to n, and I'm going to increment the size for n by 1. All right, so that's that. That's all we have to parse. We don't need to worry about candidate B. And then what we want to do is just sort votes.begin and votes.end, and then we iterate through these basically, and as we iterate through them, if they're a number, we're gonna have to do something with it. But to do a line sweep like this, we need to do something else. We need to actually create a vector that contains. Let's go way to do this. Vector. Yeah, I should do this up here though. So I need to create a vector int, and this will be my events. And then what we do is, if votes is less than 0, I don't want to add to events, but else if votes I is, I guess, less than n, then we want to add it. So we want to do events.pushback, and we want to push back the votes I and the index. And then we can do sort on the events, which will sort it according to the value, so the votes I. And so then we'll just do this. We'll just for event EV and events, and then EV is going to have the index associated with and its index. So what we want to do is we want to say if ds.ufind for EV0. So if this is equal to n, so what does it mean if it's equal to n? That means that that vote happened, but it happened in like a that means that that means that when I found the root for this index, right? We're saying these represent the index values. We say, oh wait, it's equal to n. That means that that vote was for candidate A, right? And I say, okay, well if this is for candidate A, then I want to union it And that'll be I'll union this with n, I guess, and return sizes ds.sizes n. After struct definition. Okay, so let's just go through some of the maybe minor mistakes that were made in compilation. Okay. Oh, my eyes hurt. Oops, my goodness. I'm forgetting to put the U in front of everything. Okay. Uh, this one, wrong answer. Okay, so let's print out, um, votes I, D, which is going to be basically, so it's going to be I and then votes I, except it's going to be EV0 and EV1. That was the index. Okay. And just add all this into here. 3. So we have EV3. What the fuck? Wait. EV01. So we have 1. So 1 is here. Oh, wait a second. What did I do wrong? EV1, EV0. This is 1. So what do you think for 1? What's its parent gonna be? So it should be 6. Is that correct? One. So we have 1, and we set the parent to 1. To be 5. I'm a bit confused. What's going on? What's wrong here? It shouldn't be 6 for 1. You find a 1. Okay, so let's just debug for a little bit. See that I did right. See here. Votes 3, 1, 1, 5, 6. So 5 maps to 6, doesn't it? So I need to make sure that parents of n is equal to n. Yeah, and then everything else we can say maps to whatever candidate. So we get 5, parent disjoint set 5. Okay, so I seem to fix that problem. Good. Now let's just kind of parse this. So this is the correct parent additionally set. So then we want to union this index value with uh, n. So, shit. When we do that, it's going to do this size thing. Okay. Since we're only going to be unioning with n, let's just do n. This is kind of weird, but yeah, plus or equal to the sizes of j. Yeah, actually, we don't even need that. We could just do this. We could just say, hey, we're going to set the parents of I to be equal to n if I doesn't equal to n, um, and then the sizes for n will just go up by 1. And then we don't even need to specify this. We do uFind. So we're only going to union if the parent I doesn't equal to n. Okay. Sure. So let's do this. I'm going to rename this to m, but that's just because I'm going to set m equal to n. And then I wonder if, it's getting close to the correct answer. I wonder if, can you do this? I don't know if that works. Okay, I don't think you can do that. I got confused between the two variables. Okay. So this one, size should be 0 at the beginning, right? Yeah. Here we update the size. The heck? I don't know why I did that. And then here we set the parent to be n. So we're union. So let's print out I. I is 6. We're using EV1. EV1 is 3. Oh, that's good. So yeah, it's not equal. That's good. So it's going to do this. It's going to set its parent to 6, and then we're good. 0. Why is 0's parent 5? Or sorry, 2. Yeah, 0's parent. Wait, I'm getting confused between my two values. Yeah, so this one should point to the wrong parent. I don't know why it says it has the parent is 5 for 0. Or for 2. No, the parent for 2. 0, 1, 2 is 2 is 5. It should be n plus 1. So what is that? It's I and then ds.parents I. So 5 points to itself and 1 points to 5. So the size is 1. Right, because we've already added 1 into it, right? Or 1 was already added into it. 0, 2, 3, 4, 5, 6 have not been processed. So now we consider oh, I see the problem. So you want to do ufind. So we want to do is a little different. We want to say int j equals ufind I, and then we want to say, if j is not equal, then set the parents of I equal to n, but do not do the other way around. Okay, so this is accepted. This is the tricky part about this problem really is while I'm using like a unifying data structure, I'm using disjoint sets. I really had to figure out, I guess, how do you put it? I really had to determine how to really use unified data structure for this specific problem. I'm still wrong here. Why would it be wrong here? Let me see. So here I'm guessing that we have an array that's size 3, so 3 is a vote for this. So 1 votes for him, right? Now 0, 2, 0. So this is index 2. This is index 2. The value is 0. So I say, okay, value is 0, so it's going to point to whatever 0 points to. But I don't know what 0 points to. Ah, okay. Now I see what the big issue is here. My algorithm is not going to work. So we're going to have to modify it a little bit. We're going to have to consider, I think, more of a general like approach. I think the tricky part here is going to be, so yeah, I think we're going to set all the parents. I think we're going to do the regular one. We're going to do iota. Like this. And we need to resize this like this. And then we need to set the sizes to be 1, except for these two. And then parents, we're not going to do that. So I guess I'm going to do this. Okay, and then here we do ufind, so we find its parents, and here we do union. And then what we're going to do different is we're going to see, hey, should they be part of the same disjoint set? Well, they're not right now, but they should be part of the same disjoint set. So what I do is I'm going to do if size is j, if size is I is greater than size is j, I'm going to swap I and j. So what we're going to do is we're going to attach everything to I. So we're going to say the parents of j, I. And this is kind of weird what I'm doing, but I'm asserting that basically whatever the size is, I'm asserting that I want to basically say take node j, and j is a disjoint set, right? There's a disjoint set with that root value, and that has a smaller size, or sorry, it has a larger size. So I'm saying attach the larger size to I, which is smaller, because, well, here I check if size I is actually greater, I swap. So I is always guaranteed to be smaller. So this is attaching the larger disjoint set to the smaller disjoint set's root value, root node. And then basically we want to increment the size of I to be plus or equal to j. Size is a j. We'll update the size of the smaller one. Okay, so that's what we do. It's kind of reverse logic. It's not it's not usually the most efficient way to do unifying, but it works for here. I think everything else is good. So in terms of evaluating events, now it doesn't even matter, right? It doesn't even matter now. So I'm not even going to do that. If votes is less than 0, though, I should union it with n, right? ds.union I with n. So that's what I'm going to do. I'm going to union it with n. N is guaranteed to be a smaller size because I said equals 0. So I should just attach it to the disjoint set that's associated with n. And yeah, we're just going to return the size of n. And we don't need to do this. And then we just say for int I equals 0, I less than I plus plus. And then we just say, hey, if votes I is greater than or equal to 0 and votes I is less than n, we're going to do this. So what are we going to do? We're going to evaluate it. So how do we evaluate this thing? Well, we need to consider the fact that we want to take votes I, and we want to union it. So we want to do something like ds.union votes I. Sorry. So the votes should be the same, right? So votes I should be the same as whatever this current index is, if that makes sense, right? It's just saying like take the value at this vote here. Otherwise, the vote index I made the same vote. So this index I should make the same vote as this index, and then that's it, I guess. You union them, and then ooh, this might not always work. I think I can think of some edge. I think I just thought of an edge case where this might not work. Actually, doesn't work for this edge case. So one should, let's do this. Let's print, let's say for int I equals 0, I less than n plus 2, I plus plus, printf. I'll do this, and then I, I'm gonna do this, but let's just think about what we're doing if any of our logic makes sense. And we need to see out I. Okay, let's think about what we're doing here. The first value that we compute, first thing we do is this. We look at this and what do we see? We see that we're looking at index 0. Now, index 0 here corresponds to a vote. He's going to vote the same as wherever 1 is. So let's look at our parents though before we do anything. So the parents of 0 points is zeros. So it's in its own disjoint set. So let's keep track of what's in what set. 1 is in the same set as 3. Makes sense because it was negative. 2 is in its own disjoint set, and 4 is in its own disjoint set. And 4, of course, it will always be candidate B. Now here we look and we see that the first element that we really uh, compute is, I'm a little confused. Actually, wait a second. When I do votes I, it's going to say this one, yeah, this one should be connected to this vote. So when we do 1, it's going to take 1 into votes, which is equal to the value there is, I believe, uh, uh, okay, the value is -1. So I actually want the index for that value. Okay, I want the index. Okay. Shoot, no! Okay, hold on. Still solving this problem. Let me go back to here. Okay, so I decided that this should be votes I, and then I. Why is it wrong? So here we have this, right? So we have 2 is connected to 2, right? So let's just write out. So we have 0, we have 5 and 1, we have 2, we have 3, we have 4, we have 5, and we have 6. 5 right there. So the first thing we do is we're going to take the first element, which is 2. So we're going to want to union 2 with its index. So its index is 0. So I'm going to union 0 with 2, which what's so bad about doing that? I don't think there's anything bad about doing that. So now I remove 0. 0 is now union with 2. It's in its disjoint set. Next one is -1. So we're just going to ignore that one. And then the next one is going to be 5. I think 5 we're also going to um, did I say I attached 1 to 5? Yeah, I attached 1 to 5. Index 2 we ignore. We don't have to ignore index 2. We could say um, yeah, we could do this. So what this will do is hold on. So we do this, else if votes I is going to equal to n, then you want to do ds union. I don't think this really matters, but we could union. I think I'm unioning +1. I think I decided that that one represents um, everything. Um, Yeah, so we could do that. So what happens is when we go to 2 here, so see we're at index 2. So index 2 is going to say, well, the value is 5. Oh, should be the index. There we go. Okay, so it's going to say, hey, the value is 5. So we're going to take the 2 and attach it to the 6. We're going to attach the disjoint set at 2. So that means that 2, let's see, so after we evaluate this, 2 points to 6. So 2 points to 6, 0 points to 2, 1 is, so 0, 2, and 6 are in the same disjoint set. 1 and 5 are in the same disjoint set. 3 and 4 are in their own disjoint set. Now we evaluate 3. So 3 is gonna be 1 and 0, 1, and the index is 3. So we're going to union those two. Well, if we're going to union 3 with 1, that means 3 should be added to 1, right? So let's see if we do that. We say the parents of 3 is currently here. So what should the parents be equal to? It should be equal to 5, right? So it doesn't attach it like that. It attach it like this. So we have this parents, and then should probably do this for one more time and run that. And then basically what's going to happen is we go to the last value, which is going to be a 3 with its index, which is 4. So if it's going to be pointing to the same thing, then, oh, it messed up. Hmm. So I can see where it messed up. It messed up with 4 somehow. So we get to index 4, and we currently have this. Okay, so we can see what's wrong. We can see that somehow 4 is still in its own world. Maybe we want to investigate what's going on here. Alright, so let's do this. Let's see what happened. So this is what we get. So we get the root is 5, right? So we're going to attach 1 to 5. We're going to attach 2 to 0. We're going to attach 2 to 6. We're going to take. Wait, why is I 5? Hmm. Let's do this. I just want to have it so it makes more sense. Okay, so I is 1 to 5, I is 2, j is 2. So we're going to be attaching 0 to 2, we're attaching 2 to 6. Here we have 3, and we're going to say, hey, let's attach 3 to 1. So the root of 1 is actually 5, which is fine. And then let's say we take I4 and J3. Why is 3 not pointing to 5? So what are we doing here? So let's just think about this for a minute. So when we have 3 and 1, we know that 1 points to 5, right? So 1 and 5 is size, oh, it's size 1. Um, I mean, so I guess there's two ways to do this. You could, at the end, you could just iterate through, I guess. Like let's say let's print out sizes. Print f sizes. So it's gonna be I ds dot sizes I. So sizes 2, 3. So it's 3. But the parent needs to be 5. Otherwise, I have to iterate through that entire like disjoint set. I mean, I think I should be able to do like this. I should be able to do like ds u fine in, and then like that. Yeah, that's actually accepted. I don't think I have a problem with that. And actually, let's just make our logic back to how we used to have it, which is we attach the larger ones to the smaller ones. So, yeah. So if I is larger, we're going to be setting equal to that. So this is a regular uh, ds unifying. And it worked for this case. I want to see if it will work for when we have 1, -1, 0. Okay, it works for that case. This actually should work. It's just, yeah. Okay, so perfect. The unifying did work, but I kind of had to like figure out how to use it. How long did it take me? 47 minutes. Yikes. Um, yeah, unifying was the top solution. I'm gonna upload it before I even read it. This is unbelievable solution. Dang. Yeah, you probably can do recursion. Alright, I don't think I'm actually gonna put this one on YouTube. This is so bad. I really messed up and you really just saw me kind of, I mean, working through it. At the end of the day, what I ended up really doing is kind of funny, is I ended up doing basically the normal unifying data structure, um, keeping the parents and I add on 2 extra nodes. So add on 2 extra nodes where basically n represents candidate A and n+1 represents candidate B. So I just added on these two disjoint sets so that basically whenever we try to find the parent, so okay, I'll go on why I do that. And then I set the sizes to 1, but the sizes for candidate A and candidate B, this represents the number of votes, which should be 0. So that's just like a fact, right? There's no, but the other ones we say the disjoint set is size 1, but the disjoint set for candidate A and candidate B is 0. There's nothing in there. This is a union find, so this is just going to find, this is a union union. So this will actually union them, and it uses the sizes, so it's going to attach the smaller disjoint set to the larger disjoint set. And you update the parents and everything. And you return true. I did Boolean. Technically, I didn't need Boolean in this problem, but sometimes you want Boolean because you want to know if you actually union it or not. Which is actually related to a problem I did recently, Kruskal's algorithm for minimum spanning tree, because you want to know if you want to add it to the minimum cost. Sure, that does make sense what I said there. And then so unifying DS and vote size. So if the votes are less than 0, let's just add it to the union. Let's just union it with n because it's going to be a vote for candidate A. Can we union with n plus 1? Yeah, we can. So actually, I should probably improve this. Else if votes I is greater than or equal to n, ds dot union I n plus 1. So I'm just saying, hey, this vote is actually for candidate B. So let's put him into that disjoint set. So B is part of that disjoint set. Here we just kind of evaluate everything which meets the otherwise condition, and basically we're going to union it. We're going to union that index with the node, because the index represents the node. That's what I'm doing. So this is my node. The unique identifier for my node is basically an integer. We can just do 0, 1, 2, 3, and so on. So it's just any integer. So if we have an index that is 3, we say, okay, well, that's my node. And I want to union it with whatever node is votes I. So whatever the value is at this index, that's going to represent the node that it should be part of this joint set with. So when we union that, we do that, and it's going to do the sizes. And then at the bottom, to actually get what we want to do is we want to find the disjoint set that contains A, which is n. The disjoint set that contains A is the set that's a vote for candidate A. The size of that set will give us our answer. Now to find the size of the set appropriately, the size only updates at the root nodes correctly. So we have to basically do a ds.ufind because ds.ufind will find us the root node for candidate A for the disjoint set that it's within. And by having that root node, we then get the size, and then that's the size of that disjoint set that contains candidate A, and those are all the votes for candidate A. So maybe I'll upload this to YouTube just because I think my explanation at the end is not good, but I feel like I have a pretty good grasp. Um, Man, that's crazy though. I should have just went with a regular unify at the beginning. I don't know why I was doing like that whole, like I was like, okay, let me just union it with candidate A. I was trying to keep candidate A as the root node. That's what I was trying to do originally. I was just trying to keep it as the root node, so all I had to do was return the DS sizes for candidate A. But I mean, why not just not keep it as a root node and just find the root node that it's in? Just find the disjoint set that it's in, and then I mean, this isn't bad time complexity because we're doing path compression, we're doing the rank by sizes. These optimizations are really going to keep our disjoint sets flat. So this isn't like time intensive. So, or it's not unoptimized. It is definitely optimized. Um, I think that's it. But yeah, that's how I would find the recursive vote for this problem. And what did they do? Ah, like a linked list. What do they mean by form a connection like a linked list? I mean, yeah, I mean, this is kind of like a linked list. I guess, wait, does someone actually use linked lists? I don't see anybody saying that they use linked lists. It looks like there's unifying. He just uses recursion, not really use the unifying data structure. Yeah, you could do probably recursion if you add some type of optimization. This is weird. I thought this should be less than 0. Oh, this is visited. Yeah, you have to give a visited vector and stuff. So you can determine which node he belongs in. Um, okay, well, it's not going to be 0, it's not going to be 1 initially. Oh, I see what he's doing. So using visited, he's keeping track of if he should actually like iterate down that path. So he's using recursion. So, but if numbers are greater than less than 0, it's pretty easy. You set visit 0 and you do this. If it's greater than or equal to, you just do that. Else, you're gonna have to do the recursion, where basically it's gonna keep going until it reaches an endpoint. One of these. Or one of this. What if it doesn't reach an endpoint? Oh, well, it will, because if you reach an endpoint like this, you're just going to return visit 0. So you find one of those endpoints and you return it, and then you increment uh, based on either you're going to increment if it is 0, you're going to increment A by 1. If it is 1, you increment B by 1. Oh, yeah, this is a good solution. Did I upload it? Yeah, that's a good solution. Let me just think, why did I not take that approach? I guess I didn't take that approach because I just made the observation in the unit, the disjoint data sets, and whatever disjoint set it's it's in will mean that it is that person. It just made a lot of sense to me. But it's also true that you can just recursively kind of go through there. And yeah, none of this is going to be bad. It's probably maybe even faster. Okay, I think that's all I'm going to do there. Um, should I do the recursion? The recursion is very simple. I don't think I'm going to do it. I'm going to put this as a review.